Take a look. This is an asteroid observed during a close approach to Earth taken just a few weeks ago using radar. Asteroid 2014 JO25 came within 1.2 million miles of Earth. It was a kilometer, or 2/3 of a mile wide, the largest to come so close to our planet in the past 13 years. Hello, I'm Gay Yee Hill at NASA's Jet Propulsion Laboratory in Pasadena, California. NASA takes planetary defense and the hunt for asteroids and comets very seriously. NASA-funded projects account for over 90% of worldwide efforts to find, track, and characterize near-Earth objects that get too close for comfort. Tiny asteroids hit our atmosphere all the time, producing meteors or fireballs. This chart shows the hundreds of significant fireballs detected by U.S. government sensors from 1988 until now. It doesn't happen often, but bigger asteroids hit Earth too. It happened a few years ago. A 20-meter asteroid exploded in the atmosphere above Chelyabinsk, Russia. So it's important to be on the lookout. To start things off, let's give you a simplified explanation of how we hunt for space rocks.
How do we spot near-Earth asteroids? To start, survey telescopes scan the sky. When multiple pictures of the same spot show a speck that's moving, computers automatically check it against a database of known objects. If there's no match, it gets added to a list of objects to confirm. And if it looks like it'll pass very close to us, we give it top priority. Then it's time to call in reinforcements. More astronomers from NASA, other institutions, and even the amateur community submit additional observations. Each new data point helps refine the projected path, and this asteroid is going to fly right on by. All the info will be posted online, so it can continue to be tracked and monitored. Nice work, Planetary Defense Team. Keep watching the skies.
Now, NASA is directed by Congress to find 90% of asteroids 460 feet, that's 140 meters, or greater in size. NASA's Planetary Defense Coordination Office is responsible for finding, tracking, and characterizing potentially hazardous asteroids and comets coming near Earth. Lindley Johnson is the agency's Planetary Defense Officer, and Kelly Fast is the manager of the Near-Earth Object Observations Program. They join us now live from NASA headquarters in Washington, D.C., where all NASA planetary defense efforts are managed. Hi, Lindley. Hi, Kelly. Well, let's start out with a question.
Hi.
Let's start off with a question for Lindley. What exactly is NASA doing to protect Earth from dangerous asteroids and comets?
Well, Gay, that's the whole purpose behind our Planetary Defense Coordination Office, is to oversee the efforts of NASA and our observatories that are finding, tracking, and characterizing near-Earth objects, and to work with other government agencies to develop a response if we happen to find one that is on an impact trajectory with the Earth. We work with the Federal Emergency Management Agency and other government agencies to develop the plans and the strategies that would be used to respond to a detected impactor. But the most important part of our business is to find them. We have to find them to be able to do anything about them. So our main priority is to find them as early as we can, and that's what the Near-Earth Object Observations Program is all about.
All right, so a question for Kelly. How are we finding them?
Well, Gay, NASA funds observatories to survey the skies each clear night to try to find these near-Earth objects, to discover them. And then we also fund a number of astronomers to follow up those discoveries, to try to get more observations of the positions of those objects to better understand how they're moving. Now, all of those observations from the people we fund and anybody observing around the world go to the Minor Planet Center, where they catalog and keep all those observations, but also they do a calculation of the orbit based on how those objects are moving to try to figure out where it's going to be in the future, and if there is a near-term impact risk to Earth, they will let NASA know about it. Now also JPL's Center for Near-Earth Object Studies, they also take those positions, those observations, and they do precision orbit calculation, looking at where those asteroids will be in the near term, but also into the future, decades into the future, because if there was something that posed an impact risk, you'd want to know about it well ahead of time so that you could plan your response to it.
And Kelly, are we alone in this whole process? Are other countries involved at all?
Oh yeah, there are other countries involved, and in fact there is an International Asteroid Warning Network that is a UN-sanctioned group, and NASA is a signatory to that group, and it's a group involving space agencies, national institutes, and observatories that coordinate on the search, the discovery, follow-up, characterization, and orbit determination for these objects so that we have all the information that's possible out there contributing to the task. And so yes, there is significant international participation.
So Lindley, one more question. If there is a dangerous asteroid and it's on a collision course with Earth, can we really do anything about it?
Well, that would depend on how big it is and how much time we have before the predicted impact. We would assess the size of the object and try to determine what the mass is, and that would determine what techniques might be able to be used on it. And we have, as part of our program, developing those kind of capabilities. But it all depends on how much time we have. If we only have days or weeks, that's not enough time to mount a space mission to deflect it in space. And so we would just have to prepare with FEMA to take the impact if it was on U.S. territory. So the key to our program is to find them early.
All right. So we have just a few more minutes, and I'd like to take some time for a couple of social media questions. I have one for Lindley first. David and others on Twitter are asking, are there any near-Earth objects that pose a danger to Earth?
Well, of the catalog that we have now, over 16,000 near-Earth objects, there's none that have any significant probability of impact in the Earth. Yes, there are objects that will come near the Earth, but our orbit determination folks out there at JPL, as a matter of fact, have shown that the probability of any of those is really low. So there is no immediate threat to the Earth being impacted by the objects that we know about, but we have a lot more of them to find.
All right, here's another one. This one's for Kelly. Lisa on Twitter wants to know, if there was an asteroid headed for Earth, would we be told or would NASA keep it quiet? And Khalid asks, would you tweet it?
Oh, absolutely. The public would be told. In fact, it wouldn't be possible even to keep it quiet because we coordinate with astronomers all over the world, over the internet, and so the information would be out there. And also all of the observations, as we said, go to the Minor Planet Center, and it's on their website, and then the predictions that are determined out at the Center for Near-Earth Object Studies at JPL, it's on their website. So the information is out there, and we have a communication plan here too at NASA to communicate within our government and with other governments. So absolutely, this would go out to the public, and eventually it would end up on Twitter too.
All right. So Lindley, Kelly, thank you so much. We will be checking in with you again later on in the show. And you can find out more about NASA's Planetary Defense Coordination Office by going to nasa.gov/planetary defense. As you heard earlier, NASA has to be on a constant lookout for potentially hazardous space rocks. The goal is to discover them early enough to be able to do something about them. On average, NASA-sponsored projects spot about 5 near-Earth objects a night and fine-tune the orbits of many more. NASA has adapted the NEOWISE Space Telescope to survey the skies, but the real workhorses are unique ground telescopes at the Catalina Sky Survey on Mount Lemmon, Arizona, and the Panoramic Survey Telescope and Rapid Response System. It's called Pan-STARRS, located on Haleakala, Hawaii.
Catalina Sky Survey and other survey programs are really sort of the start of the whole planetary protection ecosystem. It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. In order to find a near-Earth asteroid, we take 4 images of a patch of sky separated by about 5 minutes.
And we take those 4 images and we blink them really fast, and it creates this little animation. So we can see that the stars in the background are static, as they should be, and if there's anything that's moving, it'll pop out.
And our software compares those images and identifies things that are not moving, which are stars, and removes those, identifies things that are transient from frame to frame, and tries to link those up.
We've probably seen about 1 million asteroids in the last 7 years that the Pan-STARRS has been operating. It's like picking a needle out of a haystack. We're looking for distinctive motion, and when we see distinctive motion in asteroids, we report them to the Minor Planet Center. The Minor Planet Center is the sort of world clearinghouse for near-Earth asteroids.
The Center for NEO Studies takes the observations from the Minor Planet Center and computes the high precision orbits that we use to make predictions. CNEOS is also kind of an early warning system for newly discovered asteroids. We take the early data and we compute whether or not that asteroid could hit the Earth. If there's a chance, we'll send out an early warning, an alert for follow-up observations so that we can get more data, and then we would know perhaps whether it can hit the Earth or not.
Asteroid impacts are a fact of life. The Earth has been impacted by asteroids continually through its history.
We saw in 2013 in Russia a fairly small, by the standards of what we're finding, asteroid did hit the Earth. I feel a little bit like a guardian of the planet and doing my bit to try to protect people. It is a long-term process. It's going to take many, many years to find all of the dangerous asteroids.
The goal is to find near-Earth asteroids before they find us.
Well, tracking asteroids takes a worldwide effort. Here's a map of NASA-sponsored projects, but there's more to it than this. Add in all the observers, amateurs, and professionals all over the world, and now there are hundreds of additional eyes looking for asteroids all around the planet. These observers report their asteroid sightings to the Minor Planet Center in Cambridge, Massachusetts. That is a key player in planetary defense. The Minor Planet Center shares the information with astronomers worldwide about potentially hazardous objects. This allows for multiple observations of the same asteroid. Matt Holman is the director of the Minor Planet Center, and he joins us live now. Hi, Matt.
Hi, Kay.
All right. So you told me earlier this is all about following all the dots. So tell me exactly, what is the MPC?
The MPC, or the Minor Planet Center, is the world's clearinghouse for asteroid observations. We get observations of asteroids from hundreds, even thousands of different observatories, and we collect all those data together, distribute it to everyone who needs it or anyone who's interested. But we're also busying ourselves trying to determine which of those asteroid observations correspond to something that urgently needs follow-up observations.
Well, tell me why you even need a clearinghouse for all of these objects. Why is it necessary?
Well, there's so many people involved. It really would not be efficient to have them try to distribute their data to each other. It's much more efficient if they just send it all to us. Then we can bring it together, and we're trying to see if people have kind of incidentally observed the same object, and we can then collate those data and very quickly feed it back to them to say, okay, these are the things that need even more observations.
All right, so it's a central contact, so you work more efficiently. Can you go ahead and just walk me through the process? How does it all work?
Well, on any given night, the Minor Planet Center receives something like 100,000 individual observations of asteroids. And we ask ourselves immediately this question so constantly, which of these observations correspond to an object that we've seen before, and which of them correspond to something that's a new discovery, potentially a hazardous near-Earth object. Believe it or not, 90% of the time, we know what those objects are. We've seen them before, and we have very precisely determined orbits. We can take those 90% and set them aside and focus our attention on the remaining 10% to try to determine if those are potentially hazardous near-Earth objects or garden variety main belt asteroids.
So how do you tell the difference between the main belt asteroids, which are far, far away, and the ones that are actually kind of close?
Well, as Richard Wainscoat kind of suggested, we use the pattern of motion on the sky. Let me give you an analogy. So imagine you're in a car and you're driving along the road and you look out the window. You look at the fence posts. Those fence posts will appear to be moving very, very quickly. If you look at the trees behind the fence posts, they'll appear to be moving less quickly. And if you look at the mountains way in the background, they won't appear to be moving at all. In fact, none of those things are moving. It's the car that's moving. And the apparent rate of motion is a proxy for distance. The things that are close to you appear to be moving more quickly. And that's really what's going on with asteroids too. It's something we call parallax. So the set of dots that are really moving quickly along the sky, those are very likely to be things that are pretty close to the Earth, and that's what we concentrate on.
So if you find something that needs a little bit more double checking, how do you tell your observers?
Well, we have something called the NEO confirmation page. It's a website that the Minor Planet Center is constantly updating, and so that's where we maintain a prioritized list of objects that need additional observations.
All right. Well, we have a little bit of time left, and I have a social media question for you. This one is from Mr. Marmite, and he asks, what's the largest asteroid you've found so far?
Well, the largest asteroids are really in the category of dwarf planets. Those are, Ceres and Vesta. Those are things that were, have been found really, they were 1801, and they're even earlier archival observations. So those are hundreds of kilometers diameter.
All right. Well, we learned a lot, Matt. Thank you so much for joining us.
My pleasure.
All right. And if you would like to learn more, you can check out the Minor Planet Center. It is the website, that is. It is minorplanetcenter.net. October 6, 2008 was a day when NASA's asteroid hunting team was put to the test. The Catalina Sky Survey team spotted an asteroid that eventually would hit Earth just 19 hours before it was predicted to enter the atmosphere. The Near-Earth Objects team and astronomers all over the world sprang into action. Their observations allowed us to figure out exactly where and when the object would hit. At only a few meters across, it posed no danger. It was small and posed no threat. On October 7, 2008, with officials alerted, asteroid TC3 plunged through our atmosphere and exploded 23 miles above the remote desert in the Sudan. Hundreds of meteorites were later recovered. Now, this was the first time an asteroid was spotted and its location calculated prior to hitting Earth's atmosphere. The system worked. NASA's Center for Near-Earth Object Studies here at the Jet Propulsion Laboratory played a big role. The center computes high-precision objects of near-Earth objects It predicts the future path and assesses whether or not they'll actually impact the Earth. Paul Chodas is the manager of CNEOS. What was that day like for TC3?
That was an exciting day, believe me, and it was all compressed into a single day because it was discovered. We had to run the numbers, we had to realize it's going to hit the Earth, and then we had to figure out where it's going to hit the Earth, notify people, and encourage more observations, all compressed into one day. Fortunately, we knew it was small. That was the first question to ask, and we could see that it was small.
But it must have been just gathering together and picking up the phone call and hearing. I mean, you guys just jumped on it, everybody.
Yeah, our team, all the teams did. The Minor Planet Center, our team, and Lindy Johnson, of course, was involved in communicating this to the higher ups at NASA and in our government. So it was a busy day for everyone.
And why do you say that this was a real test and you guys passed?
Well, our calculations early on indicated it would hit in the Nubian Desert in Sudan, and so we identified the location early, and as we got more and more observations, we identified even the ground track so well that 2 months later, when some astronomers went out to look for the meteorites, we told them exactly where to find them. There they were, right on the path.
Okay, so it is the job of CNEOS, or the center, to figure out the orbit. And I think we should also explain to some people don't realize that, you know, near-Earth objects are orbiting the sun just like Earth is, and what you're figuring out is the orbit of this body and whether or not it'll one day intersect with Earth's orbit.
That's right. The near-Earth objects orbit the sun just like the planets, and they're on ellipses, and sometimes some of those ellipses come very close to the Earth's orbit. If there's an intersection of the orbits, then the next question is, well, will the Earth ever be there when the asteroid gets there? And that's kind of a very precision calculation that we have to run, and we want to do that many decades into the future. Apophis was an early example of that. Back in 2004, the orbit of Apophis looked like there was a chance that Apophis, which is a large asteroid.
I remember that.
Remember that? It was 1,000 feet across. It looked like in 2029 there was a chance that it could hit the Earth at that intersection point. And we were worried the impact probability kept getting a little higher and a little higher as we took more and more observations.
So let's take Apophis as an example. Very early on, I remember hearing the reports, it looks like there's a 4% chance that it could hit. And then as the time went by, then, well, maybe not. And then finally, there was a report saying absolutely not. Was NASA wrong at the start?
No, because we add data. We get more and more information. We make our projections. It's kind of like shining a flashlight, actually.
And we have an image that we could probably put up.
Yeah, yeah. So we would say, here's what it looks like in 2029. We think the asteroid could pass somewhere within the ellipse. And look, the Earth is within the ellipse. We get a probability of maybe it was 2% there. And then a day later, we get a little more data. And the next step, there's another ellipse. And look, it's even more likely to hit the Earth as you get more data, 4% now. But then we found some more observations actually in the archives of the same, of Apophis, and we ran the calculation again, and we get an even more precise prediction, and now look, the Earth is no longer inside the ellipse, so it can't hit.
So it's a matter of getting more and more information. How do you get that information to dial in the orbit and get a more exact idea?
What I like to say is we take all the numbers and we plot the path. You know, and so we're trying to see in the future how close it can come. Basically, we're plotting the path. We're running the numbers in high precision.
All right, so when you're running the numbers on all these sightings that are coming in every single day, how do you figure out and how do you give an early warning to folks and flag them that, this is something to keep an eye on, that's not going to be a problem for at least 100 years? I mean, how do you do that?
Well, we do calculate a probability, and we have two systems to do this. One is what we call a Sentry system, which runs a very long-term 100-year calculation, running the numbers and seeing how close the asteroids could get. We have a short-term system for the NEOCP, the Near-Earth Object Confirmation page that Matt just mentioned. These are for brand newly discovered objects that just got discovered in very little data, but we'd like to know, objects are usually discovered when they're close to the Earth. Could it hit the Earth, even before we've even confirmed the object? So that's a short-term impact hazard calculation. That's the SCOUT system. So we run the numbers both in short-term and long-term.
All right, and you keep track of all the sightings, and we can actually put up the number that you have cited so far.
Well, this is NASA, and in fact, the entire catalog is now at 16,245 asteroids. That's the blue graph there, and in 2017, which will be on the right axis there, you can see we're up past 16,000. We're seeing them at about 1,800 per year right now.
Wow.
Now, some people are concerned. They say, look how fast we're discovering them. Why are all of a sudden asteroids hitting the Earth? That wasn't happening before, was it? It was. We're just getting better at finding them. So we want to keep that discovery rate increasing.
All right. Well, I have a social media question for you. Bob wants to know, how exactly do you know the size of passing asteroids?
They're only a point of light in these telescopes.
Absolutely.
So all we know is how bright they are. So we have to assume a certain reflectivity. We're seeing them by reflected light. So we assume they're kind of as reflective as 14% of the sunshine is being reflected. So we calculate a rough size just based on brightness.
All right. Well, thank you so much, Paul. And we have a website for you. If you want more information on CNEOS, go to cneos.jpl.nasa.gov. NASA relies on trusted astronomers to do follow-up observations to confirm if a near-Earth object is really there and to help us refine the orbit. One follow-up observer is Robert Holmes. Bob started as a volunteer observer, but he's so good, NASA now pays him to hunt asteroids full-time. He's one of the world's most prolific observers. How does he do it? We went to his home in Illinois farm country to find out.
We do follow-up observations with NASA's Near-Earth Object Observations program. All night long, I'm running big telescopes. One's a 24-inch, a 30-inch, and a 32-inch, and then the 50-inch is my biggest telescope. Having 4 telescopes allows me really to do 4 times as much work as the typical observatory that just has 1 telescope. So it is a huge advantage. I work on a nightly basis, and I use these telescopes to look at asteroids. We do follow-up observations for the discoveries that are made by the large sky surveys. By looking at these asteroids and measuring these asteroids, we can determine what their possibilities of actually hitting the Earth in the future are going to be. NASA provides coordinates of specific objects that they need observations on. I'm going to punch in the coordinates here. And I'm doing this remotely from inside a control room, not at the telescope. And so we look these objects up and then use those coordinates to look at a tiny piece of the sky that this object happens to be in. And then we follow those objects and define and refine orbits for those objects and reduce the uncertainty of where it's going to go in the near future. I started off as a volunteer in 2006. It's just blossomed into a full-time opportunity to work for NASA under their grant program, where I'm now doing this every single clear night. Now we're starting the observing run for 2017 KK3. You don't build a telescope that's this big without being passionate about what you do. I'm really driven to be a part of a program that's important and has importance to the future. And we're not talking about next year or the year after. We're talking about asteroids that could potentially hit the Earth 100 years from now. And the work we do today may make a difference 100 years from now.
Like Bob Holmes, the Magdalena Ridge Observatory does follow-up observations. It's located 10,600 feet in the mountains near Socorro, New Mexico. Magdalena also characterizes asteroids. How fast the asteroid is spinning, what kind of shape it has, and what's it made out of? How big is it? The observatory has a fast telescope capable of tracking rockets, asteroids, even space junk. Eileen Ryan is the director of the telescope, and she joins us now via Skype. Hi, Eileen.
Hello, Gay.
So explain to me this fast telescope. What do you mean by that? I mean, can it whip in a direction and track something really quickly? Is it the f-stop? What are we talking about?
Well, actually, we're talking about the telescope motion. It can move 10 times faster than a normal astronomical telescope, and that's pretty fast. So we are at an advantage when we're looking at asteroids that come very close to the Earth, because they can also move very rapidly through the sky. So if we want to demonstrate this, we can watch a movie that we took of an asteroid that came very close to the Earth in November 2015, asteroid 2015 VY105. So the bright central dot in the movie is what our 2.4 meter telescope is locked on and tracking. And as you can see, the streaks that are going by, they're background stars that the asteroid is rapidly speeding by. So pretty fast. And it's pretty amazing that we can look at this and analyze close approaching asteroids. But what's most interesting about the movie, if you look at the final frame of the movie, we have captured asteroid VY105 coming so close to the Earth that it actually passed through our geosynchronous satellite zone. So if you watch the movie for the final frame, you can see an odd angled streak at the bottom of the frame, and that's not a star streaking by, it's actually one of NASA's communications satellites. So the asteroid passed very close by this satellite as well as several others, but luckily it didn't hit.
Wow, that was very close. But as you mentioned, you know, we're looking at it, same as you, they're just little points of light. How are you able to get any characteristic information on something so small?
Well, it's actually pretty fun and amazing to realize how much we can learn from a point of light. One of the things that we study and we specialize in at MRO is looking at asteroid rotation rate. So asteroids spin on their axis as they're moving in their orbit around the sun. And so here I have a model asteroid, and you may have noticed it's not very round. Most asteroids are potato-shaped or irregularly shaped. But if we use this model to examine how could we find from a point of light or light variation a spin rate? Well, asteroids shine by reflected sunlight. So here as I rotate this model asteroid, you can see the surface area is changing. So we might have a little bit of light reflected back to the instruments on our telescope when the asteroid is in this position, and then we get a lot of light, a little bit of light, a lot of light, and a little bit. Let's look at this next movie, and we can see this schematically represented by an egg-shaped asteroid rotating. You can see as the asteroid rotates, the light is changing, and we get 2 peaks and 2 dips, which represent a rotation cycle. This is usually referred to as a light curve, this changing brightness. And when we go through this whole cycle, we get 1 rotation rate. So we can have asteroids spinning as short a time as tens of seconds to many, many hours. But we can look at this and analyze the asteroid to understand potentially its strength, whether it's a rubble pile or an intact object. And we look at the peaks and dips to see if we can also infer the actual shape of the asteroid.
I remember once when we were first talking that you see these flybys as a mission coming to you, that, you know, we work so hard to send spacecraft far, far away to explore comets and asteroids and planets, but here is this wonderful moment where they come to you and you're saying that you're hitting it with everything you've got. And so you
That's
have
right.
many instruments. What else do you find as this thing is just swinging by you? What more information can you gather?
Well, we can also do, in addition to spin rates, we want to get at everything, as you said, while we have it in our sights. So we can look at an asteroid and also determine its composition. One advantage we have at MRO is that we can mount multiple instruments at the same time on our telescope. So we can easily switch from a light-changing instrument to something called a spectrometer, which will separate the light into different wavelengths, and we can then analyze and get a fingerprint of the particular composition of an asteroid. So asteroids can be metal, rock, or combinations of the two. And as Paul Chodas mentioned earlier in the broadcast, when we know overall reflectivity based on the composition, we can get an estimate of size, which is very important. And specifically, different types of asteroids, different compositions, would require different approaches for deflection if we ever found a hazardous one that we needed to do something about while it was still in space. So a very vital information characterization and an important practical role it can play.
So getting as much information as you can so you know what you're dealing with.
Absolutely.
All right. Well, I understand you told me that there is a little side story that you have a mirror that you use. It's got a little bit of a legacy, a little bit of heritage there.
Actually, it's pretty exciting. Our telescope mirror is actually one of two spares left over from the Hubble Space Telescope program. So we have the only working spare incorporated into our telescope. The other spare went to the Smithsonian Museum in Washington, D.C. after it wasn't needed for Hubble. So we feel very honored to have such a mirror, and it performs absolutely beautifully. And so New Mexico Tech University, which runs the Magdalena Ridge Observatory, actually got it for free.
Wow, great story. I have a social media question for you, Eileen. Here it is. Many out there on social media want to know when there are close approaches by passing asteroids. Can you see them with your naked eye?
Sometimes you can. It depends on how bright they are. Most of the time, though, we need even just a small backyard telescope. Naturally, if you went outside and you looked in the night sky, you might see things of a visual magnitude of 5 or 6. Even asteroids that come very close to the Earth, we might have them being as bright as 10 or 12 on our brightness scale. So you can see them through sometimes your backyard telescope. Sometimes they're very faint still, and we need big telescopes like our 2.4-meter telescope to actually study them.
All right, Eileen, always a pleasure to talk to you. Thank you so much for helping us out today.
Thanks, Gay.
All right. At the start of this show, we showed a radar movie of asteroid 2014 JO25 made using the 70-meter antenna at Goldstone Station in the Mojave Desert. The antenna is part of NASA's Deep Space Network, which communicates with our spacecraft across the solar system from this room, in fact. But that communications dish is actually a terrific scientific instrument as well. Using it for radar gives us a chance to see asteroids in great detail. Let me introduce you now to radar scientist Marina Brozovic here at NASA's Jet Propulsion Laboratory. Hi, Marina.
Hi.
Okay, explain to us how radar works in the first place.
Well, our planetary radars are very much like the airport radars that track airplanes in the sky. But airport radars, they track airplanes that are within 60-mile radius, and our planetary radars reach much further. So we are tracking near-Earth objects that are hundreds of thousands and sometimes more than millions of miles away from Earth. And for this, you need really powerful transmitters and very large antennas, such as there's a 300-meter dish, Arecibo in Puerto Rico, and then we also have our 70-meter DSS-14 antenna at Goldstone. And so let me show you, there's like a brief animation of how radar really works. So it transmits radio waves, and these radio waves, they bounce off the asteroid, and the echo that comes back carries a lot of information about that asteroid. So for example, when we observed the asteroid Apophis during 2013 flyby, we zapped, there is a video showing how we zapped the asteroid as it was going by. We zapped it with radar, and we basically wanted to very precisely measure where it is and how fast it's moving. And we used these measurements in order to improve our orbital calculations, because better data means better orbits.
So what does radar then bring to the table?
Well, you know, radar is a little bit like a Swiss Army knife, because it reveals so much about asteroid at once. You know, in optical telescopes, asteroids are these specks of lights, but in radar images, they become worlds of their own. And you can see all these details in them. So you can, in radar images, you directly see how asteroid looks like, if it has a satellite, how large it is, how it's rotating, and we can even see surface features on it. So we see we see ridges and facets and concavities and boulders and basically all the nooks and crannies. And we have such an example. There is a video you already showed. This is the asteroid we observed a couple of months ago, 2014 JO25. So it turned out to be this 2/3 of the mile long space peanut. And we were just watching it rotate in front of our eyes during 4 hours of radar observations. And it's fascinating because you could see how this, front lobe is casting radar shadow on the back lobe, and you can see all the concavities and ridges. And if you look very carefully, there are these radar bright specks that are rotating with asteroid. And we believe these are meter-sized surface boulders. And all this is visible while the asteroid was 1.8 million miles away from Earth.
Well, it's interesting. Sometimes you can even see if there's more than one asteroid and they're together.
Yes, these are binary asteroids, and now we know, thanks to radar and optical telescopes, we know that 1 in 6 asteroids in near-Earth population, asteroids that are larger than about 140 meters in size, they have a companion. So they are, and we even found 2 triple systems. Wow. So there are actually 2 asteroids that we know of that have 2 satellites.
All right. So all of this focus has been on getting an understanding of an asteroid that may be coming to us, headed this way. But could we use this information to help us if we want to go exploring asteroids?
Absolutely. So radar observations, they have been used in the past to support spacecraft missions. And in fact, mission OSIRIS-REx, that it's on its way to rendezvous asteroid Bennu in 2018, has definitely benefited from the existing radar observations, because based on that, we had a full reconstruction of Bennu's shape. We had estimate of its size, of its spin state, and even mass. And you can imagine all this information is really useful when you are planning proximity spacecraft operations around an asteroid. It just gives you a kind of level of safety for the mission, and it also allows for you to better plan the scientific observations.
Okay, I have a social media question, and this one is someone who's trying to understand, why do asteroids have these odd names like 2014 JO25? I mean, why don't you call it Madge? Why do you have these names?
Yeah, so there is actually a good reason for it. So Minor Planet Center assigns these temporary designations, and they mean something to us. For example, 2014 JO25. 2014 means it was discovered in 2014. Letter J tells me that it was discovered in the first 2 weeks of May. And then O25, there's a little formula. That tells me that it was 639th minor planet that was discovered in that 2-week period. So there is a method to the madness.
All right, so when people see that 2014 2025, they understand.
Yes, there is actually meaning.
Thanks, Marina.
Absolutely, thank you.
light. We mentioned NASA's NEOWISE space telescope earlier. NEOWISE is a space telescope. Now, it was originally designed to image the sky in the infrared spectrum. That is the spectrum that detects heat. Now, originally, this was the WISE telescope, and it was sent to survey the skies. Then it completed its job, and it was mothballed, and then it was realized that maybe it was very good at detecting asteroids. So then it was taken out of mothballs and became the NEOWISE mission, in which it allowed us to actually search for asteroids. It's focused now to characterizing and finding near-Earth asteroids. It turns out that infrared is just a great tool for hunting space rocks, especially the dark ones that are difficult for the ground telescopes to spot. Amy Meinzer is the principal investigator for NEOWISE. Amy, can you explain to me why this is such a great tool? Why is infrared so great?
Thanks, Gay. Well, one of the great things about using different wavelengths of light to study these objects is that we learn something different and unique from each new way that we look at it. We just heard about how radar provides a whole array of useful information about asteroids. Infrared light is different from both visible light and radar in terms of what it returns to us. With visible light, we're seeing light bouncing off the surface of the asteroid and coming into our telescopes. So we're very sensitive to the properties of the surface. If the surface is really dark, it's harder to see with visible wavelengths. Whereas,
so Amy, we actually have an infrared camera in the room with you, and so what is it doing? It's just detecting the heat?
Yeah, that's right. So what you're seeing is the heat that's coming off of me. You can see that my nose is cold, my fingers are a little cold, but this is the kind of imaging that we use with the asteroids, and we look for them using their heat signatures. So this lets us see them regardless of whether they're kind of light in color on their surfaces or darker in color on their surfaces.
And how is that helpful in terms of being able to spot the asteroids?
Well, there definitely are asteroids out there in the population that we know that are made of carbonaceous materials as opposed to lighter colored stony materials. These really dark colored objects are harder to spot with visible light, but if we look for them with their heat signatures using infrared telescopes like NEOWISE, they pop out.
All right. So tell me more about NEOWISE. I tried to relay this story about that it wasn't originally sent out there to look for asteroids.
That's right. The original mission is the Wide Field Infrared Survey Explorer mission. The principal investigator is Dr. Ned Wright of UCLA. And the mission was originally designed to survey the whole sky in infrared light. To search for very bright galaxies and very cool stars. It did that beautifully. It finished its prime mission successfully. But in the process, we found that it was actually quite effective at spotting asteroids, particularly these very dark objects. So when the mission was completed in 2011, we thought that was the end of the story. But we were lucky. We were able to bring it back to life.
Absolutely not. We have a graphic that I can pull up, and it shows all the discoveries that NEOWISE has made. How many discoveries has NEOWISE made?
Right. So yeah, the graphic shows you the asteroids that we've detected since the restart of the mission in 2013. So if we include the prime mission as well as the restart years, we have a total of around 34,000 new discoveries.
34,000. All right, so we obviously have shown that this technology works. So what do we see ahead as future technology? Kind of maximizing on what we've learned.
Right. Well, one of the great things about having gotten to use this spacecraft for a new purpose, which is to search for asteroids and comets, is that we've learned a great deal about how to do this work using a space-based telescope, an infrared telescope, for discovery in large numbers. Now, the thing is, NEOWISE was never originally designed for this purpose, and all good things are going to come to an end. Eventually, the mission is going to end. It was not designed to last this long, and it really wasn't designed from the get-go for searching for asteroids. However, we've been looking at new ways to search for asteroids using a space telescope that is designed for this purpose, and we call that the Near-Earth Object Camera, or NEOCAM.
All right, and there is a picture of it.
Right, yeah. So it's basically designed to go out and spend all of its time searching for asteroids and comets that could potentially get close to the Earth. And the main difference from NEOWISE is that it's going to have a longer lifetime, it can search a much wider area of the sky, and it has modern next-generation detectors. So basically these are the camera chips that are capable of sensing the asteroids at the wavelengths where they're really bright, which is infrared.
Perfect. Well, I have a social media question, and we have gotten several about how things are named. And I understand that you have been involved in naming asteroids in the past after women who were very strong.
You know, one of the great privileges of discovering asteroids is that we do get to name them. The discoverer the IAU allows us to propose names and submit them. And if they approve them, then that's the name of the object. There's some just really fantastic people out there who I think deserve asteroid names.
Give us some examples.
Well, Malala was one. And actually, one of my colleagues, Dr. Carrie Nugent, over at Caltech, and I were talking about her, and we're just like, man, she's amazing. She needs an asteroid.
Well, yes, that is a great perk. Thank you so much, Amy.
Thank you, Gay.
Okay, so what if we identify an object that actually is headed our way? NASA has to deal with that too. Let's check in again with NASA's Planetary Defense Officer Lindley Johnson and Kelly Fass, manager of the Near-Earth Object Observation Program. So, Lindley and Kelly, we have plenty of time right now, and let's look at this step of the whole phase that you have to deal with. I mean, first of all, Kelly, say an asteroid is headed for Earth. Would we tell the public about it? People seem to really be concerned about that.
Yes, Gay, we would tell the public because, first of all, the data are public. The observations go to the Minor Planet Center. The orbit determination shows up on the websites there and on the Center for Near-Earth Object Studies. So the information would be out there to begin with. But first of all, we'd want to do a confirmation at NASA. We'd want to work with our partners in the International Asteroid Warning Network to look at orbit determination and to look at the risk of impact and the effects of the impact, and to make sure that everybody's on the same page or getting consistent answers, to have that verification so that the most accurate information is going out there. And then also at NASA, there is a notification procedure in place where there would be a notification that would go up through the NASA administrator to the White House and on to other U.S. agencies, on to Congress, and also ultimately to other countries. And so, yes, it would become very public very quickly. And so we would just want to make sure that happens in the right and accurate way.
All right. So people should be rest assured that that information would never be withheld.
Right, that's correct.
Right.
It really wouldn't, because again, it's the information is on websites, and people with the right telescopes. I mean, the skies are open, so they could look themselves.
All right. So the next question goes to Lindley. What happens next if you do see something that appears to be going to be able to impact the Earth?
Well, okay, that all depends on how big it is. You've already shown us the example of 2008 TC3, a very small object that we knew that the Earth's atmosphere would protect us from it, so we weren't too worried about it. We just wanted to determine where it was going to impact, at what time, so we could go out and collect all the meteorites, as you saw, because that's a very valuable resource for the scientists to learn more about asteroids. So it's kind of a free sample return, so to speak. But if it's a larger object, say a few tens of meters in size, that's where we have to get the other federal agencies involved and their counterparts around the world to, first of all, determine where on the Earth it's going to impact so that we can alert them. One thing about predicting asteroid impacts is that we can determine precisely the time that they're going to impact. And with observations as we take, as it comes in, we can determine a location very accurately too. And so this is kind of a unique thing for FEMA and the other emergency response community is that we can tell them the time and location of a potential disaster before it's going to happen. So there's very valuable information for them to prepare the area, the community that might be affected by it, so that populations can be evacuated and infrastructure locked down. Now, if it's bigger than that, and this is actually our main objective at the Planetary Defense Coordination Office and all of the projects that we work with, all that you've seen today, is to find an object that is large enough that it could affect a major metropolitan or a statewide area, find it far enough out in time that we have time to initiate a space mission to go out and deflect it off of that impact trajectory. We are looking at various techniques and technologies like a kinetic impactor or a gravity tractor that we could send out several years in advance to prevent the impact in the first place.
So let's take that as an example. Kelly, if there was something as big as a football stadium, is that something that can be dealt with?
Well, actually, I'm going to kick that one to Lindley and let him address that.
Okay. Lindley, if it's as big as a football stadium, is that something that we have even thought about?
Oh yes, that is the type of scenario that we are mainly looking at, because the most common hazardous asteroid that we might have to face with that we'd want to deflect in space is the size of a few hundred meters or so. And if we find it several years in advance and are able to get space missions out to it, an object that size, we only have to change the speed of the asteroid by a few centimeters per second. And if we do that several years in advance, it will not reach the same point in space at the Earth at the predicted impact time. We will have slowed it down, and so the Earth will have already passed that point in space. So that is a principle that is used in all of our various mitigation techniques. So the kinetic impactor, we just hit it hard with the spacecraft. That knocks off a few inches per second speed in its velocity and causes it to be a miss instead of a hit. The gravity tractor operates similarly in that the mutual attraction between the spacecraft and the asteroid over time slowly, using nature's tug rope, gravity, slowly tugs that asteroid off of the impact trajectory and prevents it from impacting the Earth.
So we have just a few minutes left. If we could talk about that in our last 3 minutes. The fact that asteroids are a natural hazard, and from what we're hearing all throughout this program, it's a natural hazard that appears to be preventable.
Well, that's very true. It's one of the few natural hazards, natural disasters that we know how to prevent if we detect them far enough out into the future. And so that is the objective of our program here at NASA, is find them early, as we say.
All right. So one more question for Kelly. If there were some key messages that you would want out there to tell the public, what would those key messages be regarding asteroids?
Well, like we've been hearing over and over again throughout the program, is that you want to find them early, you want to find them first, and then you can, so that you can determine what the response might be. But if you don't know they're there, you're not going to know what to do about them. However, at the same time, as I always tell people, it's not something that we're lying awake at night worrying about. I mean, we're doing what we can, and there's more that needs to be done. But I want to put it in context. I mean, we're hard at work here at NASA, and our colleagues all through the U.S. and through the world, they're working hard on the problem. But again, people shouldn't be worried and fearful if we're working on it.
And that's what I seem to be hearing, that it's possible to take a proactive sort of stance in all of this, that we do know that asteroids are out there, we do know that they could pose a real hazard, but what I'm hearing here is this is sort of a proactive approach, that if they're out there, let's find them and then let's see what we're dealing with.
Yes, Gay. Because we have a space program and we have the technologies to go out and be able to move these small bodies in space now, this is something that we can prevent. We just need to have the will to put the programs together to, first of all, find them well before the impacts, and then have the capabilities demonstrated that would be able to divert the objects. Now, one of the programs that we're trying to...
All right. Well, Lindley, thank you so much. This was a very, very informative program, and thank you so much for your information. Here are the websites once again: the Planetary Defense website, the Minor Planet Center website, and CNEOS. Thank you so much for joining us. I hope you learned something, and we hope your questions were answered. That wraps things up from here at the Jet Propulsion Laboratory.